Good evening, everyone. Sorry to fade out green onions. It's my great pleasure to welcome Armour to the department, and he's going to be talking tonight about Sugarcrete. And it is, I've been saying all day to third years, but it's such a wonderful project, and it's got even kind of more interesting in a way, because it sort of starts off in East London, sugar refinery, working at East London, and making this interesting building product, and also looking at the geometry of the pieces that go together. And then it's starting to kind of go back to the places where sugar cane actually comes from, which is kind of interesting, or makes a lot of sense. So Armour is an architect, worked for some big practices, including VR Ingalls, MVRDV, KPF. Now, thankfully, he's in the world of academia, so thank you, welcome, good. And just really pleased you're here to talk about the project. It's become a kind of iconic project in architecture schools and beyond, so I don't know whether you know that, but it is, so thank you very much.
Thank you very much. Is the sound okay? We good? Yep. Okay. Thank you very much, everyone. I'm really pleased to be here explaining Sugarcrete to such an engaging audience. Very nice to see some familiar faces as well. And I'm here to talk about the project that we have developed in the University of East London for the last 4 years, which started as a student project led by Master of Architecture students, which got in touch with the Tate Lyle, which is a sugar refinery that is close to the university. They started to engage with them looking at how to use byproducts to create construction materials, and then through the leadership of tutors, and also through an institute that we have in the university that is specialized on testing, we came up with the idea of using bio-waste bagasse, which is the byproduct of sugarcane, to create building components of different types. As we'll mention, we started from London, so we started by looking at what we had available in the refinery that was in front of us, but very soon we realized that it was not enough material and that it made much more sense, rather than producing here, exporting the technology and the know-how to communities where sugarcane grow in the global south. And that's where we are at the moment. We are calling it a global material for a global crisis, and we are aiming that it can become a change in the construction industry. As I mentioned, it's a collaboration between two different parts or parties of the university. One is the Master of Architecture at the University of East London, and another one is the Sustainability Research Institute, which is an institute within the university, but it operates independently. They do a lot of life cycle assessment consultancy externally as well, and a lot of research on biomaterials and materials in general, and they were very excited to see the application of the material for construction. So they went beyond what they were typically doing, that was testing just samples, to test elements that could become construction systems. And that's where the collaboration with architecture students became very rich, and we are continuing that in our agenda this year with the students. We are 4 people as a core team, architects by background, 2 of us material scientists, which has been key to the development of the chemistry behind the material. And then we have a PhD student and research assistant, and we are advertising for a new PhD position that is going to be working in the material as well. So if anyone is interested, please get in touch. We can send you the call. We started at the beginning looking at how are we consuming materials globally, and there is a lot of talk about how we are emitting CO2 as an industry and how we should reduce that. But something that not everybody is aware is that almost 50% of all the material that we extract globally, whether it's eroding the topsoil, cutting forest, or extracting steel and stone, 50% of it comes from the building and construction sector. And we know that to limit global warming, we need to find an alternative to it, and developing negative emission technologies, such as building with biomass, is crucial. However, biomass and biomaterials, as we understand them, at least from a Western perspective, we think that timber is a solution for many of these issues, and just by building with timber, we are creating sustainable buildings and sustainable materials. However, timber is not available in many regions of the world. And if you look at that map from the World Resource Institute, all the areas on the global south, most of Latin America, Africa, and most of Asia, including India, there is no timber industry. There are no factories that are preparing or producing cross-laminated timber, and timber is just not available for construction, which means that they are left with alternatives such as brick, concrete blocks, concrete many times imported material, high carbon materials, and almost 50% of the global built area that is going to double by 2050 is going to happen in these areas. So we thought that it was key to address this issue with different and alternative materials. We started by looking at available agricultural bio-waste and how this can be upcycled to create construction materials. And we came out with sugarcane. So it was through the collaboration with Tate Lyle, that is located close to the university, but also our own research of different stocks that are available worldwide. And sugarcane is the largest crop by production volume, and almost 1/3 of the plant biomass is left after extraction, and that's called bagasse, which is the byproduct of the industry. It's the largest bio-waste supply chain globally. The production in tons, that's the number, is astonishing. I visited a factory in India earlier this year in February as part of a research trip, and only one sugarcane industry out of almost 200 that are operating in the area, it was producing constantly almost 43 to 44 kg of waste per second. So you could get almost 100 of those blocks per second. That means that if all this bio-waste was used for construction materials, whether they are blocks or beams, they could replace the brick industry globally, which represents between 3 and 4% of the global warming potential, according to the FAO. There are alternatives, of course, and you might have heard about hempcrete and other bio-waste that are used for construction. Hempcrete is quite extended in Europe, it's used in France. Now I think that they are trying to grow more and more hemp to use it for construction materials. However, it's very limiting. So if you see that graph, the amount of sugarcane that is already available in the world is 16,000 times higher than the amount of hemp, which means if you want to match the production of sugarcane, you will need to plant an area the size of the UK with hemp, which is an area that doesn't exist at the moment in the world. So we thought that rather than tapping into existing practices, which are planting and growing to create construction material, we could look at waste and bio-waste that is already existing. Alongside the availability, there is also the CO2 absorption rate of sugarcane. It has a rapid growth that allows for CO2 absorption that is significantly higher than hemp or forestry, 50 times higher than traditional forestry, and even higher than taifa, which is another material that we are looking at for deploying similar technologies. This said, we are also looking at using different agricultural byproducts using the same formula as we have developed with sugarcane, and we are at the moment developing a taifacrete equivalent, which will be used on regions where sugarcane doesn't grow. The fibers of bagasse are quite long, especially after being milled. The milling process has 5 different mills which extract the sugar and the water from the plant, and the fibers that are left are quite long and they interlock each other very well, which allows for structural applications, and it can become a viable alternative to replace timber frame or CLT using much less land. So that's a study that we did, just comparing the amount of land that you need to create 1 square meter of CLT, 1 square meter of a timber frame wall, and 1 square meter of sugarcrete wall, and it's 10 times and 23 times less land required to create the same amount of construction. In a year, you grow a crop of sugarcane, normally seasonal. During 6 months they harvest, and then the other 6 months the plant is growing, whereas traditional forestry takes up to 50 years to be ready for harvesting. So all that sounded very well, but we also wanted to set up goals and to set up strategies that would allow us to work with the industries that are producing and harvesting sugarcane in an ethical way. The main strategy and the main goal that we set up was that we could use this material to store carbon. So this is one of the blocks that we are producing currently in India. You can pass it around if you want. And each one of these blocks, if they are produced locally, they sequester 1 kg of carbon each. That means that if this is implemented as a construction material in these areas, it could become a carbon sink, and it could become one of the largest carbon sinks in the region. And they are materials that they can last for decades, and they have been tested to different standards that demonstrate that, and that they can be part of existing construction systems as well. We also believe that we should not get this information just for academia or for commercial opportunities, but we believe that open source employment and open source communication and know-how is key to the aims of the project and of Sugarcrete. And we think that it can create export opportunities in Global South communities. So currently we are producing some of these blocks in India, and we are encouraging opportunities for exporting those blocks to the UK. We had already 2 shipments that came to the UK. We are planning a 3rd one with the idea that we reverse the export-import opportunities. And they are low-cost materials, so from the beginning we wanted to be able to compete with local materials such as clay bricks or concrete blocks. So the cost of this block that you see here is equivalent to the cost of a brick in India, which is way cheaper than in the UK. They are high-performing materials, and they can replace low-carbon, high-carbon, low-performing imports. Currently, the sugarcane industry is linear. So here you see a sugarcane field. An hectare produces around 8 tons of sugar, which equals 23 tons of bagasse and 3 tons of molasses. And they are traditionally harvested in 3 different ways. There are farmers that are just using bull carts to harvest the sugarcane, and they bring it directly to the factory. Others, they are more organized, and they have small tractors and vehicles that bring it as well to the factory. And then for larger distances, they have collection points where they have small huts, and they have small facilities where the material is stored, and from there is then taken with bigger lorries which belong to the sugarcane factory. This is in India. Each country has a different strategy. And the opportunity here is that because each farmer is working in a different way, the material could also benefit some of these collection points and can benefit some of these farmers that during half of the year almost they don't have employment opportunities because the harvesting is seasonal. The production then has a number of mills. The material is milled using different grades, and then there is, as I mentioned before, sugar, molasses, and bagasse. The bagasse is used to run the facilities, so it's burned to produce electricity that then runs the operation. Around 70% of it is reused for boilers, which means that in a way they are using biomass to run the operation. But in most of these countries, electricity is getting cheaper, and the grid is being decarbonized by introducing solar and wind energy. So that amount that is 70% every year is reducing, and the amount that is left, which at the moment is between 30 and 35%, is increasing. So they are looking actively for alternatives. There is paper, there are plates that are done out of bagasse, but they don't take enough out of the factories. The fact that you burn it, it means that you are releasing back the CO2 that was absorbed, so there is no carbon sequestration, and then you are also releasing another pollutants that are damaging the workers that are living around and working around the plantation. What we are proposing instead is to include circularity to some degree in the production of sugarcane and sugarcrete, whereas we can use that 30% remain and upcycle it to have an economical value for the communities, produce bricks or blocks or slabs that are made using very simple material, very simple machinery. They are done looking at geometries that can assist with the seismic movement. So the bricks that the block that you see there is interlocking, so it can reduce the movement of the wall in case of seismic activity, and it can be used for local plantations or to create a product that they can sell in the market. Those blocks, they are bound with lime mortar, so we are using lime mortar for putting them together and also for covering externally the blocks, which means that it's very easy to reuse them, so they can go back into the building if required, and if not, they can be crushed, and after crushing, they can be used as stabilizing the soil, or they can be mixed back into the production. Up to 30% of crushed material can be mixed back with the original mix of bagasse and lime and water and be used as part of the next round. This allows for fair trade, circularity, end-of-life reuse, and contextualization. So we are operating at the moment with different partners in different areas of the world, most of them in the global south, and we are trying to contextualize what do we do with each one of them. So this block was developed with India because they came with a brief and they thought that that was the most appropriate. We are collaborating with partners at the moment in Costa Rica, where we are developing an insulation panel which can be attached to existing systems. So that's an alternative that will be using different geometries and different processes. So being able to contextualize to where you are working is key to the success. We are using cost-effective and widely available machinery. So the blocks in India are done with a hydraulic press. They are using metal molds that allow them to unmold immediately. So you don't need to create a mold, wait for it to dry, and then in a couple of weeks unmold it. You can directly take it and put it to dry, which that's a system that we didn't develop in the university. We were casting always using timber molds, and they came out with this kind of evolution that allowed them to do 400 blocks a brick with only 2 people. So that as part of the collaboration, we always have an agreement of what is intellectual property, what is background intellectual property, and what is foreground intellectual property. And we have developed quite a lot of intellectual property with them, which means that the product now belongs to the collaboration, which is also quite unique. So it's not something that we keep ownership of in the university, but we try to open it up through licensing so other people can use it as well. What can we do as a university? So we thought at the beginning that we will be making bricks. We can obviously not make bricks, or we cannot make enough that we can create an impact globally. So we decided that the easiest would be that we support with what we know best and what we can do best. And in our case, that's testing to industry standards and testing different construction strategies and systems. So as part of the university, we have facilities at the Sustainability Research Institute that are tested internally and then verified externally with independent institutes. And the main testing that we have been doing, they have to do with the thermal conductivity, and it's been proven to have very low thermal conductivity, 007, 008, comparable to straw, cork. The highest possible fire rating, due to the binders that we are using, we have achieved class A1 on fire rating, which means that you can use it anywhere, both for cladding and for structure. We have managed to achieve a compressive strength of 5 megapascals, which is comparable to concrete blocks, which allows you to have load-bearing and non-load-bearing walls. It's lightweight and it's low density, so if you want to pass this around, you will see that it's quite light. So the weight is light enough that you can work with 100. You can take it. Yeah. You can pass it. It has still a bit of bagasse on it. It came from India a few weeks ago, so it's still not fully set. And it has very good moisture buffer value, which I don't know if you're familiar with it, but it's a property that biomaterials do very well, which means that they are able to absorb humidity from the environment. So in areas like India, where there is a lot of humidity, depending on the season, but the humidity levels can reach very high numbers, having materials that having a wall made of a material that can take part of the humidity and then release the humidity once the environment dries is key to somehow control the passive cooling and the passive heating of the space. As I mentioned, some of these testing are done internally, but then they are all verified externally. So we are working with institutes in different regions of Europe. I was mentioning as an anecdote, we tried to work with the BRE in the UK to have our sample tested there, and they didn't understand that it was one material. They wanted to test the bagasse and the binders independently, which wouldn't make any sense because we know that bagasse ignites, so the test will fail immediately, but they wouldn't accept that this material was a composite material. We need to go to an external laboratory in Europe that was used to work with biomaterials, and we were able to do it there. So there is a lot of misconception and there is a lot of misunderstanding of what biomaterials can do. And most of these testings are done for materials that are not having the same properties. They are done for concrete, they are done for brick, they are done for metal, but they are not adapted to the regimes of biomaterials. So that PhD position that we are advertising at the moment will be looking into how the standards and the testing that we have in industry at the moment will need to adapt to somehow make the most of what biomaterials offer. For instance, on the compressive strength, biomaterials, unlike concrete blocks, they have very good residual strength, which means that if you have a block of concrete and you crush it, once it breaks, it crumbles and there is nothing left in terms of strength. However, the fibers of the biomaterials, they don't disappear, they don't go anywhere, they stay there, so you can continue applying pressure and there is still a lot of strength, almost 30% of strength that is left after the machine is detecting that the material is failing. So we could add that 30% to that number. We haven't, because the test is telling you that you cannot, but in theory you could. And this testing is allowing us to go further and to support our partners. So most of the partners that we are working with, they don't have capability to test to this standard. So what we are doing the testing internally, working with bagasse that comes from different regions in the world. And then that testing is assisting them to do the verification locally. So instead of going blindly to a laboratory with different ratios and different samples, we are saying, do the sample with this ratio, utilize this pressure on the hydraulic press, and then you will get a sample that is going to pass your fire testing, so you don't need to do it 10 times. And that's proven very helpful. Some of the testing, of course, is using ISO international standards, so if you do it in one region of the world, it's valid for others, but that's not 100% true for all the areas. So some of them are covered with some of the testing that we already have, but others need to be done locally as well. We support as well with life cycle assessment. So for us, it's very important that the material is dealt in a way that can absorb carbon, because it's the main point, it's one of the goals that we have set. So we always provide life cycle assessment support as part of the collaboration. The block that you are passing around, this is the life cycle assessment that we did, A1 to A3, assuming that they are fabricated locally in India, and compared with a concrete block fabricated locally and with a clay brick fabricated locally, compared by volume, so using the same volume of material for the three of them, and is 6 times lower than clay bricks and 3 times lower than concrete blocks, and is carbon negative. So it's the only one of the three that is carbon negative. And that's the amount that is sequestered per brick. By collaborating externally, we have managed to create a network of almost 16 partners, which are hopefully they will grow at some point. Now we don't have capacity for much more, but we are doing collaborations with different areas and different regions. Each one is different, and they range from small collaborations with artists or with academics to larger commercial collaboration with companies and corporations. A lot of this was due to media exposure, so don't undermine publications and don't undermine Instagram, because we got a lot of this through social media, through publishing our work on the scene, through making sure that the work was out there, and then people just contacted us. The main collaboration with India, which has resulted in a facility that is operating and building now, creating blocks, manufacturing the blocks, was through an article on the scene. The day after, when we published, we got almost 200 emails, and one of them was from India, and they said, we want to do it. We don't understand why nobody thought about this before. Let's do it. And in a year, we managed to set up a facility with them. So combining open source with the IP framework, that's not always easy. So when we talk about open source, we said, okay, we can share the information and we can share the know-how, but depending on what do you want to use it for. If it's for a commercial aim, then it needs to be a framework that deals with the intellectual property and that deals with licensing and also distribute equally the benefits, so we can continue supporting the research in London. Part of that income is allowing us to reinvest in research and in technology support, and that means that we have a partners range which is quite wide. So as I mentioned, we are collaborating with the artists in Reunión, where they are building a wall for a community center, and we have just supply the information, and we are collaborating with them without any cost. But then we are also collaborating with commercial entities that want to produce the material, and in that case we are having a framework where we are agreeing on the way we are collaborating with them. This is kind of summarized on this diagram. This is how we are operating when it comes to finding new partners and creating new partnerships. So we start with organizing NDA, so we make sure that the intellectual property is protected to some extent. We get supply of the material to our laboratories for testing, know-how, and technical package. So we can prepare packages where we say, if you buy this material or if you buy this machinery from one of our suppliers, you can, in a month, be producing blocks, which for some people is interesting because they don't want to go through the whole process of getting to that point. Then we sign a memorandum of understanding, and there we have a partner policy that includes ethics. So we make sure that all the supply chain that we are working with is agreeing and is fulfilling the partner's policy that we have created internally at the university. And that's something that is quite important because sugarcane industry has a background of, not in all the areas, but in many areas of abuse of disparity of employers. For instance, women are very unlikely employed in sugarcane industry because it requires quite a lot of strength to cut in. In India, they are only employed for removing the leaves once the cane is cut, which is not happening in the same length of time, so automatically they have less employment opportunities. So we are trying that when we are producing the blocks, get at least the same amount of women and men, even if in India is quite challenging. And the first facility that we set up, it was not the case, but we are trying to get that in place as much as possible. Once that's agreed, we have a project agreement, so we discuss how are we going to work in terms of intellectual property. Until when do we say, okay, this intellectual property belongs to the Sugarcrete team, and then everything that we design together is foreground intellectual property that then is shared, and then it creates a new product that then is shared between that company or that institution or that partner and the team. And that means that we can get investment, we can get certification support, we can get fieldwork engagement and analysis, product development, so we can create new products that is not us saying we think that this is a good product, is more working with partners on site that they know the best what do they need, and they know the best their local markets, and improving as well the facilities and the equipment that we have at the university. So we are using part of that funding to continue improving the facilities that we have locally. We are getting quite a lot of impact globally, which for the university is one of the key parameters that the project has been successful. Impact in the sense that a lot of people are starting to use the material locally. Students around universities around the world, they are contacting us because they want to use the material for their projects. We are supporting that, but also companies that are producing or small architectural firms that want to test the material and want to do it locally, especially the ones that are a bit more hands-on. So that impact, we are trying to record and register that impact as much as possible, but a lot of it is happening without us knowing, which is beautiful in a way, but it's also quite surprising when you see it. And that impact is environmental, is social, and is economical. And now I have a couple of case studies that I wanted to show with you of how we started and where we are now with the product and with the project. The first case study is the first time that we display and kind of explain the material outside the university. It was a collaboration with the Sustainability Research Institute within the university, the Sugarcrete team, Grimshaw, so Grimshaw architects were involved on the project, and Tate Lyle, which were supplying the materials and some of the byproducts that we were using. It was a project to create an interlocking structural slab prototype, and we were collaborating with engineers from AKT2 who were actively supporting the project before, and we are still collaborating with them. And this is an image of how the project came together. Grimshaw were very interested in stereotomy and the legacy of these strategies, which started to look into how an arch or a flat arch could become a flat vault. And they were quite keen into exploring the work of albeit, which I don't know if you're familiar with. It was a French engineer that in the 17th century, 18th century developed a system that by creating elements that interlock with each other, so they are acting like a flat arch, but in both directions, you could create a flat vault without any mortar in between the elements. So they are kept together just by geometry. And drawing from the work that albeit developed, we came together with a strategy to create a number of blocks which are shaped in a way that when you turn them around and you put them close to each other, if you brace the perimeter, they stay stable. We developed a 1.2 times 1.2 slab, so it was a smaller prototype, but calculations from AK82 demonstrated that it could go up to 3 meters times 3 meters, so 9 square meters of slab without any support in the center. For this initial prototype, we used metal rods on the perimeter, so the perimeter was working in post-tension, so once all the blocks were coming together, we were passing these rods on the perimeter, tying them on the ends, and then applying the right amount of pressure until the blocks will be kept together, and then the slab could be lifted. These are some images of when we did the first demonstration at the university a couple of years ago. And something that we found out along the process is, as with any other casting materials, biomaterials, they shrink quite a lot after being casted. So a test that we did as part of the research, we casted in different, these ones are using hempcrete and silica, that's using bagasse and silica. We tested also hemp and bagasse with lime. So we tested different ratios and different options for the blocks. And we 3D scanned all of them individually, one by one, and we compared the volume after 2 weeks, after a month, after 2 months with the original 3D model. So we could assess how much shrinkage the whole system will have, which was fundamental to design a system where all the elements will come together equally. The reduction was between 5 and 10%, depending on the amount of binder that we were using, which was what we anticipated, but it was a very good use of 3D scanning technology to demonstrate how this slab will need to be accommodating for those tolerances. This is a photo of the assembly, so as you can see, the metal rods are passing around the perimeter. We located 2 at different heights. Later on, we realized that probably with 1 was enough, but for this initial prototype, we had 2 of them, and the only thing that was required to assemble the whole slab was the sort of tools, very basic and available in any other location. And the beauty is that once the slab is not required, you can just unscrew it, disassemble it, and bring it somewhere else. Individually, you can lift them. When they come together as a slab, it's quite heavy. So we thought that they will need to be assembled in a way that can be lifted easily up with a crane. So the assembly will need to happen on site. And this is the final result of the prototype that we tested. We wanted to test it for a structural load. We couldn't bring it to the laboratory, it didn't fit. So we just did a kind of in-house structural testing with all the team loading the slab. I think it was 10 of us standing on the block, and they didn't even move a millimeter. So we thought that the system worked in the same way as when you were building a cathedral, you had to stand when they were removing the formwork, and then if it stands, it stands. If not, you don't survive. Here it was not so radical, but we proved the concept with our own load. And at the moment, it's been, thanks to this collaboration with Grimshaw, we got a lot of attention. So probably you have seen the video that we did with them on the zine. And thanks to this work, we also put biomaterials to a different level. So biomaterials, ram earth, or cob walls, or blocks of unfired clay, they have been used and they have been around for many years, but they don't have a very good reputation, especially in countries in the global south. So we thought that working with an architectural firm that has the prestige of Grimshaw and developing a system that it has a lot of intelligence on the geometry and on the technology that you are using, could put the material at a different level, and then people would have interest on using this material for applications that are beyond building on a rural area in India. We then realized that bringing this to India is a challenge because it's a technology and it's a geometry that is not that easy to replicate and to manufacture. So the next project that we did, we kind of simplify this and we developed the block that you have been circulating. in the second case study that I wanted to share with you, which is an AI laboratory room in Noida, in India, for a college that is already existing, as a collaboration between the University of East London, SRI, Sugarcrete, Chemical System Technologies, which are supporting the operation locally, and the Ministry of Education of the Government of India. We co-designed the project with the Master of Architecture students at the University of East London. It was a simple room extension. The only requirement from the client side is that they wanted to use metal structure for the roof, because that way they could get the certification that they needed from the council. So the blocks were having load-bearing walls, but the load was also carried by the columns externally. The project is located, as I mentioned before, in Noida, close to Delhi. And we thought that this could be a good opportunity to do a proof of concept where the material could be deployed for the first time and where it could be monitored. So we are starting now a 12 months monitoring system, comparing the material and the performance inside the building with a control room in the same college, which is not having any insulation, just having concrete blocks. We designed 2 different blocks, so there was simplicity of manufacturing, so you only need 2 molds to create them. One was the standard block, it's the one that you have been circulating, which is the equivalent of 2 bricks, and the weight is the weight of 1 brick, so that it will be easy for a bricklayer that is used to lay bricks to use it. And then we had a corner block, which was having a cross for the intersection that was resolving the corner condition, and was also resolving when we were reaching a window or we wanted to end the wall. You didn't need to cut a brick by half, you were just using the lower block, which is 1.5. So just with 2 geometries, we were able to resolve the whole building, which means that you only need to invest in 2 molds, and you only need to explain that you have 2 typologies to workers on site, which was also fundamental for the success of the building. This is how the corner comes together. So we had a number of corner blocks, which was kept to a minimum because they are a bit more difficult to manufacture because they are a bit larger, and the rest was shorter bricks, which was the majority of them. And as you can see, it has a groove, so the profile is designed to interlock as well. So we draw inspiration from the interlocking geometries that I was showing you before. And that groove, it seems that it's doing little, but is assisting the wall in terms of seismic movement by reducing almost 20% the movement of the wall in case of seismic activity. It's also minimizing the amount of mortar that you need to put them together, and it's also assisting with the air tightness of the wall, because the air is not going through the gap, but it needs to do more, especially we are keeping a bit of an air gap in the center, so we are putting mortar only on the sides, so that area allows for an additional layer within the system. We also design a set of lintels using different binders that allow for tensile strength. So these blocks are good at compression strength, you can pile them on top of each other, but they are quite weak on tension. So we thought that we needed to design a different mix, a different ratio just for the lintels, and we designed that prototype that you see there, where it's only, again, sugarcane bagasse and silica binders, but it has a hessian mesh, which is a natural mesh on the underside, and that mesh helps almost improves the amount of load that you can put by almost 10%. So here is the testing that we did in the university. It's a 3-point load testing, so it's supported in 2 points on the sides, and then you put the load in the center, and then you measure, you add load, and you measure how much the material is deforming. And by adding that very simple mesh on the underside, it improved almost 50% the performance. This is an axo view of the window, how the elements come together, timber window, operable up and down, and then the lintels are located on the top and bottom of the windows. The top lintel, all of them are connected, so it's creating a rim beam or a belt on top of the wall for additional stability. This is a section of the building, so we were trying to create overhangs on both sides for an area for gathering, but also to protect from direct rain. We kept one of the walls exposed so we can see how it weathers, and we proposed a clerestory truss that would allow for natural ventilation through a stack effect on the top. And then there is a concrete base and a concrete upstand that is lifting the Sugarcrete wall by 150. So in moments of heavy rain, we are protected and lifted above the ground, which is typical standard practice when you are using biomaterials of ram earth. And this is me in India. So that was February last year, incredible visit. They were really welcoming. They were really looking forward to learn about the technology and to operate and build with the blocks. So it was an incredible experience to see how something that comes from academia can expand to the real world, and it can go beyond the typical sample that we see of 10, 10, 10 and become something that they can produce. They set up a production facility for 400 blocks, but they could extend it tenfold in a day, and while creating employment opportunities for plantation workers around the area. And these are some photos of the site. So this is from, I think, 2 or 3 months ago with the master bricklayers that didn't know the material, and in a couple of hours they were able to use it without any problem. And one of the quotes that we got from them is, working with the blocks feels easy, they are light but yet robust, they are practical and easy to align, which for us was very important, because if you design something that looks really good, is really complex, it works very well, but then you need a crane or you need a CNC or you need a robot to assemble, you can forget about implementation in countries where that's not available. So we thought that that ease of implementation and ease of both manufacturing but also deploying the material was fundamental. The blocks are having a lime and sand mortar in between them. Is gray, dark gray, because it's coming from granite sand from the Himalayas, and we kind of tested different widths in between blocks. The blocks are not all the same because the material tends to expand. So instead of contracting as we experience here, is the other way around, it's expanding by around 5%, but they don't expand in the same way. They expand with different ratios, which means that they are not fully aligned, so you need to allow for a bit of tolerance in between them. And I quite like this photo where you can see how the bio-waste wall is being built against the concrete frame, concrete block, and stone-clad building in a very harsh environment. So it's a parking area which is going to be transformed with green area around, and this is part of the new development. And you can see here some services that were already running, so it's very easy in these blocks to just cut, run a pipe or run electrical inside the block and then just terminate it with a bit of mortar. And that's a couple of photos which are halfway through. We finished externally with a lime render with brick dust, oil and wax for water resistant. And as I mentioned before, we are monitoring for 12 months and benchmarking for thermal values, moisture buffering, and internal acoustic reverberation. We have got very good acoustic results as well on the material. The fibers are helping the acoustic absorption, and that means that the reverberation is reduced, especially on areas where you have traditionally materials that are not that good performing. So just having a percentage of the wall built with this material will help with acoustic as well. And this is an image of the school. It's still not in use, so it's been finished a few weeks ago, so this is one of the first times that we are showing these photos. We decided to render only to the datum of above the windows, and then the rest is kept exposed. We thought that everything could be kept exposed, actually, internally. Externally, we have rendered it to waterproof it. We have received a lot of questions about termites. They are quite common in countries where we are operating, especially in India. And it's a lot of them. I think it's almost 200 different species. And we are doing tests at the moment with the Agricultural University of Hisar. It's a test that has never been done, so there is no testing regime to see how termites attack bio-waste materials. But there is a lot of research literature online on hempcrete, which is using very similar components. So we have used that as a base, and we are now getting very promising results on Sugarcrete. Some more photos of the building being finished, which is still missing all the landscape around it. And this is how the elevation works. And we have, of course, as I mentioned before, we started with that collaboration with Grimshaw. We have done a lot of work with community projects, and we are now testing thin shell structures. So we are aiming to deploy the material with different capabilities. But for us, I think that the most important is that it's not something static, it's something dynamic, and it's something that can adapt depending on who are we working with. So these are some case studies and further projects that we are doing at the moment. We are expanding the collaboration with the slab and trying to get a larger piece manufactured in Mexico for demonstrating the potential of the material in a real-life project. We have done a couple of collaborations with the Tate Institute, which is an institute that it was a social center for workers of Tate Lyle, and now it's been abandoned for several decades, and now they are going to transform the center into a community center for workers, but also for the community in Silvertown. So we designed this set of modular benches using Sugarcrete for the playground of the center, and we have used the blocks to insulate the existing walls. So we are collaborating with them as a retrofit opportunity. And this is a mock-up that we are doing in collaboration with local artists from Poland. They won the competition to build a pavilion for Burning Man, which is going to be a permanent pavilion in Burning Man. It's a new area that they are developing, and they want to use reeds that are located local to the pavilion. So we use the same technology that we are using for Sugarcrete, but just changing the crop by reeds, which are quite similar in terms of the length of the fibers and the properties that you can achieve with them. And this is our latest collaboration. It's a live co-design project with a foundation in India. After we finished the school, I think 2 months ago, we have got a lot of collaboration opportunities, and we thought this was quite relevant for both the agenda of our students, but also the social value that it brings. It's a foundation that is concerned with upskilling kids and women that left education earlier than they should have, or they didn't have education at all. So the program will look into how to encourage them to come back to education or back to productive activities. And the idea is to create a biomaterials center where biomaterials can be produced and tested locally, and people can learn about the use of biomaterials, and that through education. We will be using hybrids of Sugarcrete and bamboo for the building, and we are doing it as a live exercise with our students of Master of Architecture in the University of East London. So in a way, the project started with the student work, it went into research, it went globally, and now is going back into student work, which we think it continues the circle, and by bringing the material and the opportunities back into the realm of academia will in a way expand, but also it allows us to support collaborations with foundations like Pariatan, who they already have a site, they already have the funding, but they didn't want to do the typical building that they will do if they were designing it with the local architect there. They wanted to do something a bit more innovative that could also, the building itself could work as a kind of demonstration of what you can do if you think outside the box with materials. And that's it for what I have prepared today. These are 3 photos from my trip to India. The one on the left is a sugarcane plantation which was being harvested by the time we were there. This is how the mills are operating, so it's a vast amount of material produced per second globally in the world. And the opportunities that we can bring to the local economy by understanding how they use the material and designing with them are very large. That's the website, so all the work that we do is published and is accessible to everyone. So if you are interested, you can access, look at our website. All the reports that we produce when we do collaborations, they are uploaded there, other than the ones that have confidentiality clauses, but most of it is available to the public. So through dissemination, we are also getting a lot of interest of people working with the material and sending us how they are transforming the technology into something different. We just finished a collaboration with the Building Center Institute in Argentina, where they have replaced sugarcane bagasse by corn, which is very abundant in the country, and they have created a version of these blocks using the same geometry, but using corn, and they have used that for a building which is going to be starting soon. So we are trying to disseminate as much as possible and trying to also not to hold into the fact that it needs to be sugarcrete. It can be many different biocretes, but using the technology and the experience that we have already gathered for deploying this in different areas of the world. And I think that's it from my side. Thank you very much. I think we have some time for some questions or remarks or concerns, if you have any.
I've got the microphone.
I think they are the back.
Yeah,
Yep.
Hi, thank you. I wanted to ask you, in the project that you did in India, what did you use for your foundation layer?
The foundation is a concrete slab, so it's a concrete base. We initially planned stone and lime foundations for under the wall, but it was too complicated to get the right labor. They are used to work with a number of materials, and when you want to propose something different, it's quite challenging. So we didn't want to fight all the battles. We said, okay, let's do the base as a concrete slab, and let's just build above that 150 datum, that is the one that we established. We are now working with a local architect that is doing a lot of work with earth and is replacing earth blocks with the sugarcrete blocks, and she's always using stone and lime foundations for her project, so we are hoping that that can be the next demonstrator of how it can couple with the foundation level. But for the project that we did in India was a concrete slab.
Okay, thank you.
No worries.
Hi there. I just wanted to ask, I've got a few questions. Our studio, we're looking into biomaterials, and we're using nettles as a composite along with other binders. We've had very success with potato starch, bioresins, and the likes. But I was kind of wondering, is there anything in the processing of the bagasse that makes it so good for this material?
I think any biomaterial will act in a similar way. I think bagasse is, first is the availability. So if you want to create impact and change, you need to look at the numbers. So how much can you do with what you have? Second is the fact that it's a byproduct. So it has commercial value, but very little commercial value compared with other crops. And it's already available, it's already there. So you don't need to plant for it. So there are different crops that are also aligning with that, but not all of them have fibers that are as long and as strong as bagasse does. Binder-wise, bio binders and bioresins are a very good way forward, and depending on the application, they can have a lot of potential. But I would suggest that the first thing that you do is take a block and set it fire. Because if it burns, then you need to add something else. So that was the first, when I was starting to work with our students and we were starting to look at algae or different kind of bio-based binders, which were having very good credentials. The main issue is that once you set them fire, they don't protect. They maybe protect for a few seconds, but then the whole thing ignites. So I think that I see a lot of work on biomaterials where there are samples that are made that look very good, but I don't know if they work or not. So to me, the key question that I ask when people approach me and say, okay, we are working with biomaterials, what do you recommend? The first thing that I say is like, look, what are the industry standards for the application that you want to do? Each application is different. If it's a brick, if it's load-bearing, is one certificate. If it's non-load-bearing, it's a different certificate. If it's an insulation or acoustic panel, it's a different certificate. So think of the application, see what is the requirements that you have, and test it. You know, these are tests that if you do it in the laboratory, it's expensive and it's not easy to do, but an initial version is really easy to do in a ceramic workshop where you can just set fire to one of these blocks. So the first test that we did with our students actually was like each one was doing a different ratio and a different binder. We built 20 blocks, we put them there, and we set them fire. And it's like, fine, it looks beautiful, but if it ignites, we cannot work with it. because in a way, I think that we also need to be conscious that the responsibility that we have when we promote biomaterials, we need to understand that what we are selling is safe, and that we can make sure that it's going to work and that it's not going to create issues long term. It has already enough issues of acceptance. So if we create more challenges and more questions that are unanswered, we are not making we are not working as one, let's say. So I think that my advice when we were using bagasse and when we were using either lime, calcium carbonate, sodium silicate, we have different binders that we are testing in different ratios, but all of them, they have a key component, that is that to some extent they protect from fire spread.
Perfect, thank you.
No worries.
Thank you. I guess my question is to do with the carbon calculations that you were doing to do with Sugarcrete, because in my mind, if you're like shipping something from one side of the world to the other, then you kind of run into problems of, well, actually shipping it's producing tons of CO2 as well. So I don't know if that was part of your calculations or not. And to build on that, if it was, would there be other kind of substitutions you could do in places where it's less feasible to do Sugarcrete and have that be a thing?
Yeah, so the LCA that I was showing was for the Indian product in the Indian market, manufactured in India. So we were assuming that you will manufacture where they are doing, which is local to the plantations, so that transportation is only from the plantation to the manufacturing facility, which were a few kilometers. We have done the same exercise for bringing the blocks into the UK, and obviously most of that carbon storing will go into the transportation. And that's why we think that the same formula can be applied to other biomaterials, whereas taifa that is abundant here, corn that is abundant in Argentina. So we are trying to adapt also to other alternatives. But the main aim that we have is that this is produced locally. So it can create exporting opportunities, and it's still carbon negative if you bring it to the UK. So it's still 10 times better than a brick that is imported from India, and the UK is importing almost 10% of the bricks from India at the moment. So whether you are importing a clay brick or you are importing a Sugarcrete block, is going to have a massive impact on your carbon footprint when it comes to the UK. But our aim is not for exporting and making the blocks travel around the world, although if that creates opportunities for partners in the Global South, we think is still valid, but more to work locally and disseminate the technology locally so it can be produced where the plant grows. In Europe, we have sugarcane in Spain, in France, in Portugal, so there is production. It's not comparable with the amount that is produced in India, but we are at the moment doing a collaboration with a designer in Barcelona to design acoustic panels, which they are going to be exhibited in the Milan Design Week. I didn't bring it because we still don't have the right photo, so I will bring it for the next presentation. And the sugarcane bagasse, we are getting it from Spain. So if you consider the transportation from Spain to the UK is much less, so probably they will still be carbon negative by the time they reach the UK, especially by boat. Something that is adding complexity to that calculation is that at the moment the carbon allocation of bagasse in the whole sugar industry is very little because the economical value is very little. So when you sequester CO2 and you plant sugarcane, that carbon that you produce while processing the sugarcane, it gets allocated to the sugar because the sugar has more value than the bagasse. Very, very little goes to the bagasse because the bagasse has very little value. If this becomes successful and the bagasse has more value, then more carbon will be allocated to there. So I think that LCA is not something that you do and is just static. It's something that you need to continue changing as the market evolves and as the way you are producing changes.
Thank you. Thanks.
Thank you.
With your calculations, is it like CO2 that you calculate or CO2e?
It's the equivalent. Okay. Yeah, and it was divided in two different parts. One was the biogenic CO2, so the CO2 that has to do with the plant absorbing the CO2 from the atmosphere, and then the CO2 of the production and of the binders.
Thank you very much.
No worries.
Thank you. Just curious about how you can attach components onto the face of the brick, like heavy kitchen cabinets and stuff.
Yeah.
And the screws won't just rip out the wall.
That's a very good question, and it was one of the first things that we were asked. So we prepared a short PDF that is on our website of how to drill. You can drill it with the drill. It drills very well, and you can just use the same fixing that you will use on plasterboard or on timber. And it takes quite a lot of load because the blocks are very good on compression. So if you compress them with more load, it's not a problem. So all the boards for the school, all the equipment that the school requires is just attached to the walls directly. And in terms of fixing, well, what we are proposing is that they have a finish that is a render. So you will need to drill through the render and then all the way to the block. And then once you reach the block, then you can just, with a Fisher connection, you can just very easily hang or attach elements. We also were considering services, so how do you run services, electrical, water, and it's very easy as well to open kind of a gap on the material of a certain depth and then run services there and then render it again. And because they are quite wide, even if you take 4 or 5 centimeters of the block, the wall is not being affected. It's a very good question, thank you.
I'll be back.
What are the cost differences between a traditional brick and Sugarcrete?
Sorry?
Production costs.
Production
between
cost,
the
yeah.
traditional brick and Sugarcrete, what's the difference?
So that was the first point of the brief. We were told we are very happy to do it, but we need to be cost competitive because otherwise we cannot present this to the Ministry of Education and say you can build your school with this material, because they would say if it costs more than what we are doing now, we are not paying for it. So we were asked to, as much as possible, minimize the binder, which is the expensive part on the block, and optimize the production process so we wouldn't need to, we could keep the price as low as possible. At the moment, the cost of producing one block is equivalent to the cost of producing 2 bricks, which by volume they are equal. The difference is that if you have a brick wall and you want to achieve the same thermal performance, you will need to add insulation. But if you build a wall with Sugarcrete, the wall itself performs already and insulates enough to meet British standards.
Thank you.
No worries.
I asked you earlier about durability. Mm-hmm. I wonder if you could talk a bit more about that, because it seems like when we keep comparing it to a clay brick, mm-hmm. How does it compare in terms of durability?
So externally, we are advising that they are rendered with lime renders, and we are using lime renders that have been there for generations and are still standing. The issue is that not everybody knows how to do lime render properly, especially externally when it needs to add clay dust and needs to add pigments and elements that can keep it waterproof for longer. So the main challenge that we're having at the moment is how do we go back to techniques that were widespread before, but at the moment it's not easy to find labor in India that can do properly a lime render. So we managed for the first building, and we are hoping that on our next collaborations that's established as the norm, and that render is going to be the one that determines the durability externally, especially when it comes to wind, when it comes to water. We have tested the blocks in a weathering accelerated chamber. So it's a chamber where you put the block and you test it for a week, and that equals 2 years, or a month, and that equals 5 years. And that's accelerating, exposing to the elements, and we have got very good results out of it without any render, just the block itself. However, we think that rendering externally is a safer option. Internally, we think it can be kept exposed, and we don't see problems with durability. The initial blocks that we did, they have already 4 years. They have been outdoors, and they are as good as the first day when we make them. But obviously, it's a novel product, and it's a question that we get asked very often, and that's why doing demonstrators and doing buildings that are using the material for the first time is, we think, is fundamental to the success of the project. But I think that there is a lot of course, work being done already with hempcrete, for instance, buildings that are done with hempcrete for many years, and when you compare what we have achieved in terms of durability with a hempcrete block, we are above the data that they have obtained. So we think that by doing that comparison with materials that are already in the market for a while, we can somehow answer those questions. That's easy to answer here within our context because we know what hempcrete is and we have seen it, but in India, for them, it's as foreign as sugarcrete. So it's an additional challenge.
Is that something that worries you? Because you imagine, let's hope this is a big success, and you know, you're kind of releasing it into the wild then, aren't you? And then, you know, potentially people are going to be building with this material, but they won't bother to render, or they won't put in the overhanging roof. Or
they will render with a cement render, which it means that the wall doesn't breathe as well as it does if you do a lime render. Yes, that's a risk that we need to take. I think that the best we can do is suggest best practice, and that's the information we have on our website of how we advise that the material is used. But if you want to spread it, you also risk people using it in ways that are not as appropriate as they should be. But that happens with blocks, but in India also happens with bricks. The quality control of bricks in India is not the one that we have in the UK. The ones they send to the UK, yes, but the ones that are there, is many times the walls are not as straight as they should, and we saw a lot of walls that were collapsing because they were not properly made, and that's a lot of load, which is also very dangerous. So I think that that's something that is already happening, but additionally, the buildings that they are not having insulation properties, they are very difficult to use in summer. Some of the comments that we got from the principal of the school is that the rooms that they were traditionally using in summer, in certain periods, they were unable to use them anymore. They are reaching above 50 degrees. It gets really humid as well, and it's a space that is not climatized because they don't have the systems. So I think that this is, yes, it's durability and making sure that the material is as good as possible, but it's also looking at what the alternative is. And the alternative sometimes is not as good as we think, or as we assume that it will be, because we think that it's a block or a brick that is used with a ventilated chamber with insulation inside, but it's not the case. Yep.
Thank you very much. What an amazing talk, and you must be exhausted. But I just had a question. It was really good to hear that you have a policy partnership, and I recognise that you're working with a byproduct of sugar. But I just wonder what your policy partnership covers in terms of sort of people working with sugarcane, because it is problematic, isn't it?
Mm-hmm. It is, and it has a background that is even more problematic, and especially when you think about how it relates to colonization and to
child labour.
It's a crop that child labour, women labour, is a crop that kind of extended as especially British French were colonized in Spanish initially as well, and it's been associated with slave labor as well, and that was how it was done at the very beginning. At the moment our partners policy is the partners policy of the university, so it's quite strict, and of course safeguarding is fundamental to the policy. But we are aware that that's not a policy that all the companies have implemented. working with companies such as Tate Lyle, which are doing a lot for ethical and for safeguarding, and for working with partners that they can assure that they meet the policy of their corporation, which is an international corporation, is something that has been very helpful for us. So we can make sure that the supply chain that we are using for our testing and for our products that we do in London, it goes through safeguarding and through the policies that Tate & Lyle has, that are in some cases even more strict than the universities. So I think that that gives us some confidence. But the first thing that we do when we start working with a new partner is to send the partner policy and the questionnaire, and to make them sign that questionnaire, and for them to share their policy on safeguarding as well, and on equal employment opportunities.
So if you're buying that biomass, can you actually use that as a lever to encourage companies to have good work policies? I mean, can you actually say, well, I suppose, I'm seeing it as a positive lever to kind of pressuring companies to have good policies towards their workers and safe, because you talked about safety, but sugarcane is quite a dangerous sort of product, isn't it, to work with?
Yes, and there are many employees that they lose fingers cutting it, and then they cannot go back to employment, so they are left they don't know very well what to do after that, and we are aware of those issues, and that's key to the work that we are doing. And the policies that we sign with the sugarcane facilities or factories that we are working with, they tend to align with the policies that they have in place. Whether they are implemented locally is something that is very difficult to check for us. What we are making sure is that any material that we are using that is going to be used for the Sugarcrete project is certified to comply with the policy that we have in place. And that means that all the employment opportunities that we are creating and all the work that is done to produce the blocks aligns with that policy. So in a way, it can also trigger that companies that perhaps at the moment they are not having those policies in place, if they want to collaborate with us, we are asking them to comply with them. So we had that case in some companies, especially in South America, where they didn't have policy in place, and we asked them, we are happy to collaborate with you, but you need to put a policy in place that aligns with ours, or that at least in certain points we can find a common ground, which is not always easy. And sometimes that common ground cannot be, you cannot change the whole industry at once, but if you change one aspect of it, or if you kind of demonstrate that that change continue to produce value, it might inspire others as well. So I think it's probably one step at a time, but we are, I mean, from the beginning we were aware that this crop that has political, social, and historical implications, and we are hoping that by producing in a way that is more ethical, some of these companies which are not having the best practices can see that it can be done in a different way, or can perhaps change their practices if we are putting that as a requirement, let's say, and if they want to collaborate with us. The reality as well is that each country operates in a different way. So in India, for instance, the plantations are owned by the workers, whereas in Brazil they are owned by the factories. So in India you are having almost 50,000 workers that are supplying one sugarcane factory, and it's up to the worker how the field is. So they can have policies of, if I'm buying the sugarcane from you, you need to comply with this. But then they need to really be on site to make sure that that compliance is implemented. And I think it's improving, but there is still a lot of work to be done there.
Yeah. Look, thank you so much for tonight's talk. Fantastic talk, and thanks for answering so many detailed and good questions. And just to say that Alma has very kindly given us a donation of this one block that will sit in our materials library upstairs, so you're very welcome to have a look at it. But don't do too much structural testing on that block. But but thanks very much. Fantastic talk. Thank you.
Thank you, Will, very much. Yeah.